Welcome to Chapter 4 of Digital Communication, Bandpass Modulation and Demodulation. Module 5 includes Quaternary phase shift keying, that is QPSK modulation. QPSK is 4-array modulation. So there are 4 symbols 00, 01, 10 and 11. For getting that 4 symbols, 2 bits are going to be taken together. So the total duration of each symbol will be 2 TB second. The symbols are 00, 01, 10, 11. So now we want to get 4 different phase modulated signals to represent 00, 01, 10 and 11. For a previous case, that is a BPSK, there were only 2 symbols. So the phase difference was 180 degree because the total phase is considered as 360 degree. So 360 by 2. So 180 degree was the case for a BPSK. Now there are 4 symbols. So 360 divided by 4. So 90 degree phase difference is needed for 2 adjacent symbols. QPSK can be generated using phase quadrature carriers sin omega 0t and cos omega 0t. Sin omega 0t is multiplied with the plus minus 1, so we will get sin and minus sin. Cos omega 0t is multiplied with the plus minus 1, we will get plus cos and minus cos. So we are going to get 4 different signals, sin, cos, minus cos with a 90 degree phase difference. Sin and minus sin can be considered as a BPSK. Cos and minus cos also can be considered as BPSK. So QPSK can be generated from 2 BPSK signals. For QPSK, phase difference will be 90 degree. So 4-array modulation is known as QPSK due to the phase quadrature carriers are used for the generation of 4-array PSK. That is why it is called QPSK. Expression for QPSK is BOT root PS sin omega 0t plus BET root PS cos omega 0t. So some of the important differences compared to BPSK is, it is written here O and E. That O stands for odd bit and E stands for even bit. Out of these 2 bits, first bit is considered as odd bit, second bit is considered as even bit. In some textbook it is written BIT and BQT, that is in phase signal and quadrature phase signal. So here I am using odd bit and even bit. First bit is odd bit, second bit is even bit. That odd bit is multiplied with the sin omega 0t, even bit is multiplied with the cos omega 0t. Even though it is 00, 01, 10, 11, the corresponding voltages are plus 1 and minus 1. So this will be plus or minus 1, non-return to 0, polar format. And this is also non-return to 0 polar format with amplitudes plus minus 1 volt. Here amplitude is written root PS. Normally we always write root 2 PS, but here root PS is written, and the reason is there is an addition. Once it is root PS, the signal power will be amplitude square by 2, that is PS by 2, and remaining PS by 2 will get from here. So after addition, the signal power of QPSK is always PS. That is why instead of root 2 PS, root PS is written. BOT and BET are non-return to 0 polar format with amplitudes plus minus 1 volt and interval 2 TB second. That is a very important difference compared to binary transmission. Now the duration of non-return to 0 polar format is 2 TB second because we are taking 2 bits together. Total duration will be 2 TB second. Due to this expansion, we are able to get half bandwidth for QPSK transmission. So block diagram shows that B of t is converted to odd bit and even bit using serial input parallel output with a clock period of 2 TB second. If the clock period is 2 TB second, we will get 2 parallel bits with a duration 2 TB second. If the clock period is a 3 TB second, we will get 3 parallel bits with a duration 3 TB second. That is the function of serial input parallel output. Here our requirement is 2 parallel bits, that is why clock period is equal to 2 TB second. It can be generalized to n TB second for getting n parallel bits. According to that expression, odd bit is multiplied with the root ps sin omega 0t, even bit is multiplied with the cos root ps cos omega 0t. This is considered as one BPSK modulator. Second multiplier is considered as another BPSK modulator. So from two BPSK signal, we are going to generate QPSK signal. That expression is again written here, BOT root ps sin omega 0t plus BET root ps cos omega 0t. These are the four combinations and the corresponding voltages are written here. 0, 0 will be represented as -1, -1, and then do the substitution here. -1 into root ps sin omega 0t plus -1 into root ps cos omega 0t. This is the signal for 0, 0 transmission. Next for 0, 1, -1 and +1, substitute in that expression. So it will be minus root ps sin omega 0t plus root ps cos omega 0t. Similarly for 1, 0, the voltages are 1 and -1. After substitution, root ps sin omega 0t plus minus root ps cos omega 0t. For 1, 1, both will be positive. And for each signal, the transmitted power will be ps. When you are taking the average of QPSK transmitted power, it will be ps. Power of this signal is ps by 2. Power of this signal will be ps by 2. So ps by 2 plus ps by 2, the power will be ps. How to calculate power? That is amplitude square by 2. Amplitude square is ps by 2, ps by 2. That is why the power of this portion is ps by 2. Power of second portion is ps by 2. Total power will be ps. These four signals are represented here as a vector representation with a reference axis root ps cos omega 0t, root ps cos omega 0t and plus 90 degree, that is cos theta plus 90 degrees minus sin theta, that is why it is written here minus root ps sin omega 0t. Opposite vector is minus root ps cos omega 0t and opposite vector is plus root ps sin omega 0t. These are the four vectors before addition. Now depends upon the combination, there is an addition. For 0, 0, minus root ps sin omega 0t, that is here minus root ps sin omega 0t plus minus root ps cos omega 0t. So this vector and this vector are going to be added. The resultant vector is here with an amplitude of root 2 ps, and that is for 0, 0. Similarly, second combination, minus sine and plus cos. This is minus sine, this axis is plus cos. Addition of these two, this is a resultant vector for the combination 0, 1 with amplitude root 2 ps. This is for 1, 0, this is for 1, 1. These four vectors are the QPSK vectors with amplitude root 2 ps. And an important advantage we are getting here is adjacent combination differ by only one bit. This is 0, 0, next 0, 1, next not 1, 0, it is 1, 1, and next combination 1, 0. Adjacent combination differ by one bit. That is why it is called gray coded QPSK. So due to this gray coding, probability of error can be minimized. When you are transmitting 0, 0, the most probable reception will be 0, 0. The next probable reception will be 0, 1 or 1, 0, because these two are the adjacent vectors. And if 0, 0 is received as 0, 1 or 1, 0, there is only one bit error. And the least probable case is 0, 0 can be received as 1, 1. Then only we will get 2-bit error. That's the advantage of a gray coding. So using gray coding technique, probability of error can be minimized. Now each QPSK vector can be written in terms of cos omega 0t. Amplitude is root 2 ps. With respect to cos omega 0t, pi by 4 phase difference. So this vector we are able to express like this, root 2 ps cos omega 0t plus pi by 4. It is written here. Root 2 ps cos of omega 0t plus pi by 4. Similarly, the second vector can be written here axis cos omega 0t plus 3 pi by 4. So root 2 ps cos omega 0t plus 3 pi by 4. It is written here. Similarly, all four vectors can be written. Root 2 ps cos of omega 0t plus 5 pi by 4, that is this vector. Root 2 ps cos omega 0t plus 7 pi by 4, this vector. Finally, all these vectors can be represented as a single expression. V QPSK t is equal to root 2 ps cos of omega 0t plus 2i plus 1 into pi by 4. That expression shows that from two BPSK signals, we are able to generate QPSK with constant amplitude. Amplitude is always root 2 ps. Constant frequency, there is no frequency variation, it's always omega 0, but there is only phase difference. and the phase difference will be 90 degree between two adjacent vectors. So that's a QPSK expression. Root 2 ps cos of omega 0 t plus 2i plus 1 into pi by 4. Substitute I is equal to 0. It will be cos omega 0 t plus pi by 4, this vector. Second vector, substitute I is equal to 1. That will be 3 pi by 4, this vector. Next substitution 2, that is 5 pi by 4. Next substitution 3, 7 pi by 4. So in all these 4 vectors having same amplitude, same frequency, only phase difference is there, and that phase difference will be 90 degree. Now how to draw that QPSK waveform? Here first I am showing a cosine wave. Cos 0 is equal to 1. So this waveform is root 2 ps cos omega 0 t, root 2 ps. So at t is equal to 0, it will be cos 0 into cos 0 is equal to 1 into root 2 ps. So amplitude is root 2 ps. And this is 2 pi. So for different phase value, the amplitude is calculated. Cos pi by 4. Cos pi by 4 is 1 by root 2. 1 by root 2 into root 2 ps. It will be root ps. So like this, first point, second point, third point, fourth point, all these 4 points are important with respect to our previous expression, because we got 4 QPSK vectors like this. Root 2 ps cos omega 0 t plus pi by 4 plus 3 pi by 4 plus 5 pi by 4 plus 7 pi by 4. So for 0 1 combination, the signal is going to start from this point. For 0 0, this will be the starting point. 1 0, this will be the starting point, and 1 1, this will be the starting point. Now we can see how to draw the waveform. So an example is written here. B of t is equal to 0 0 0 1 1 0 1 1. So I am just giving some numbers like this 1 2 3 4 5 6 7 8 to differentiate between odd bit and even bit. 1 3 5 7 are odd bits. 2 4 6 8 are even bits. Because when you are taking the combination will be like this. First combination 0 0, next combination 0 1, next combination 1 0, fourth combination 1 1. In each combination, first bit is odd bit, second bit is even bit. So this is serial input, parallel output, BOT and BET. That is input, serial input is converted to parallel bits with the duration of each bit will be 2 TB second. So here I am writing 0 to 2 TB, that is a first bit, and then 0 to 2 TB second bit. First bit and second bits are 0 0, that is a 0 0. Third and fourth 0 1, that is a 0 1. Next combination 1 0, here it is 1 0. Next combination 1 1 1 1. Here it is represented with the plus 1 voltage and minus 1 voltage. It is written here, minus 1 voltage and plus 1 voltage. So at every 2 TB second the combination can change. Now how to draw the final waveform, that is QPSK waveform. Otherwise the multiplication will be like this. This is multiplied with the sin omega 0 t. This signal is multiplied with the cos omega 0 t. So we will get a sin or minus sign. Here we will get cos or minus cos, and we go for an addition. You can do that algebraic addition. We will get the third waveform. But here I am showing an easy method to draw QPSK waveform. Take the first combination. The first combination is 0 0. And see here 0 0 from where we should start. For 0 0 starting point should be minus root ps. So start from minus root ps. Minus root ps. Then start from here and complete one full cycle. So start from here, completing one cycle like this. From where we start, there you end. One cycle is completed. So this I made for a TB second, but here the duration is 2 TB second. That is why 2 cycles are completed. So start from minus root ps, ending minus root ps, one cycle is completed. Let's go for one more cycle. So 2 cycles are completed per 2 TB second. So there is no hard and fast rule. 2 cycles should be completed. 1 cycle, 2 cycle, 3 cycle, any number of integer number of cycles you complete. So here 2 cycles are completed. So starting point we are getting from here 0 0. That is the first combination. That is why starting from minus root ps. So start from minus root ps, then touching the peak negative value minus root 2 ps, then touching root 2 ps peak positive value back to minus root ps. One cycle is completed. So like that 2 cycles are completed over that first 2 TB second. For first 2 TB second the combination is 0 0. For 0 0 only this is a starting point. Next combination is 0 1. Check here for 0 1 what is the starting value. For 0 1 from where we will start? From root ps. from root PS, then down direction like this. So the same thing I am doing here. Start from root PS, down, completing root PS. Again one more cycle is completed. So 2 cycles are completed over this 2 TB second. Third combination is 1 0. 1 0, this is a starting point, and after that it is going up. So here also I am doing the same thing. Start from minus root PS, then up. 1 cycle is completed, then go for one more cycle. So 2 cycles are completed. Last combination is 1 1. 1 1, we will start from plus root PS, then up direction. Plus root PS, up direction. 1 cycle is completed, then one more cycle is completed. So this is QPSK waveform. So the important one is we should know for each symbol interval what is a combination, then for each combination from where we should start the waveform. Then the waveform can be completed without difficulty. There are transition you can see at every 2 TB second. Previously we studied this type of sudden change can generate high frequencies. These high frequencies can interfere another communication channel that is known as inter-channel interference, that is ICI. And this interference will be maximum if the phase transition is 180 degree. You can see here we are getting 180 degree. Because 0 degree there is no discontinuity. For 360 degree also there is no discontinuity. So the discontinuity will be maximum if the phase transition is 180 degree. So if we are able to avoid this 180 degree transition, we are able to say that inter-channel interference is less. We can see later how it is possible. Here the phase transition is calculated like this. First combination is 0 0, second combination is 0 1. See the corner what you have written from 0 0, that is 0 0, from 0 0 to 0 1. This is clockwise direction. From 0 0 to 0 1, it's a minus 90 degrees. So that is it's minus 90 degrees written here. Next combination is 0 1 to 1 0. 0 1 to 1 0, that is opposite. If it is opposite, minus 180 or plus 180, there is no difference. So I am writing here 180. Next combination 1 0 to 1 1. 1 0 to 1 1. 1 0 to 1 1 is anti-clockwise direction. Anti-clockwise direction it will be plus 90. So plus 90 is written here. That is same as minus 270 degree. So the possible phase transitions are plus 90 degree, minus 90 degree and 180 degree at every 2 TB second. This is a case of a QPSK. In QPSK, phase transition can occur at every 2 TB second, and the possible phase transitions are plus 90 degree, minus 90 degree and 180 degree. And this 180 is creating maximum discontinuity and maximum inter-channel interference, at the same time inter-symbol interference also, that is ICI and ISI. Here I am explaining a solution to avoid 180 degree phase transition. That QPSK is known as offset QPSK or staggered QPSK. Offset. There is an offset of TB second between odd bit and even bit. So due to that offset, odd bit and even bit are not going to change simultaneously, and then 180 degree can be avoided. So here again the same combination is written here 0 0 0 1 1 0 1 1, and the first I am taking odd bit. So I am showing here odd bit from minus TB to TB, then third bit TB to 3 TB, fifth bit 3 TB to 5 TB, seventh bit 5 TB to 7 TB. And instead of starting even bit also at the same time, even bit is starting after TB second. So odd bit and even bit are not starting simultaneously. Naturally, there is always a difference of TB second between first bit and second bit. Just maintain the difference, that's all. So first bit is starting from this point. After TB second, start the second bit. So even bit is starting from 0 to 2 TB, first bit, that is bit number 2. Then 2 TB to 4 TB, bit number 4. 4 TB to 6 TB, bit number 6. 6 TB to 8 TB, bit number 8. So this is the meaning of that offset. Offset existing between odd bit and even bit. For the previous case, offset was 0. Here offset is equal to TB second. Due to this offset, the advantage is odd bit and even bit cannot change simultaneously. You can see the result here. Here odd bit is changing, but at the same time even bit cannot change. Even bit can change only here. But when even bit is changing, odd bit cannot change. If both bits are not changing simultaneously, we never get 180 degree phase transition, only plus 90 or minus 90 degree. Now how to draw the waveform? At every TB second you see the combination. First TB there is no combination, so leave there. Second TB combination is 0 0, and previously we got the answer for 0 0 starting from minus root PS. One cycle is completed. Then see the next combination. Next combination is again 0 0. So from minus root PS, one cycle is completed. See the third combination. Third combination is 0 1. For 0 1, starting point will be plus root PS. So plus root PS, one cycle is completed. Next combination is 1 1. For 1 1, the waveform should start from plus root PS but up direction. So that is completed one cycle. This you can see the previous QPSK waveform. Next is 1 0 1 0 from minus root PS up direction. One cycle is completed. Next combination is also 1 0. So start from minus root PS, one cycle is completed. Next combination is 1 1 1 1, like this case 1 1. Start from plus root PS, one cycle is completed. At the last bit interval there is no combination, so leave that one. So we completed 1 2 3 4 5 6 7. 7 bit interval we got the pair and we got the offset QPSK waveform. That is known as OQPSK waveform. Now see the advantage what we are getting. At every TB second we will verify phase changes are occurring or not. First 0 0, next 0 0, there is no phase change. From 0 0 to 0 1, that is clear from here. 0 0 to 0 1, clockwise direction always minus, anti-clockwise direction it will be plus. From 0 0 to 0 1, it's minus 90 degrees written here. Next combination 0 1 and next 1 1, 0 1 to 1 1, 0 1 to 1 1, again minus 90 degree. Next 1 1 to 1 0, 1 1 to 1 0, again minus 90 degree. And then 1 0 to 1 0, there is no transition. Whenever there is no transition, you can see there is no discontinuity. This is a requirement to avoid inter-channel interference. That is, high frequency generation can be avoided if the signals can be generated without any discontinuity. And 1 0 to 1 1, 1 0 to 1 1, 1 0 to 1 1 is anti-clockwise direction, that is plus 90 degree. So now the possible phase transitions are plus or minus 90 degree only. You never get a 180 degree transition. So due to this reason, less ICI and less ISA compared to QPSK modulation. So this is the advantage of offset QPSK over QPSK. But surely we are able to say one disadvantage. Here transition can occur at every TB second. Every TB second transition can occur. But in the previous case, transition can occur only at every 2 TB second. So if you count the number of transitions, it is actually more here. There the number of transitions are less. Number of transition occurring only at every 2 TB second. Here transition can occur at every TB second. But here we never get a 180 degree transition. Only plus or minus 90 degree transition. That also will generate high frequencies, but compared to 180 it is less. Coherent receiver. This type of receiver we already studied. For a BPSK, it was square bandpass filter with a 2 omega 0 and frequency divided by 2. Instead of that 2, write everywhere 4. For a QPSK, the received signal is passing through raised to 4, then bandpass filter with a center frequency 4 omega naught, and then frequency divider divided by 4 for regenerating sin omega 0t and cos omega 0t. Then only we are able to say our receiver is coherent receiver. Because for a coherent receiver, we need synchronized carrier from the received signal. Here I am showing how the carrier is going to be regenerated. The received signal is plus or minus 1 root ps sin omega 0t plus or minus 1 root ps cos omega 0t. That's a received signal. The received signal is first squared here. A square plus b square plus 2ab. So a square is ps sin square omega 0t. B square is ps cos square omega 0t plus 2ab. That is plus or minus 1 into 2 ps sin omega 0t cos omega 0t. After squaring, we can see these sin omega 0t plus cos square omega 0t will become 1. So we are not able to get a signal without plus minus 1. That is why one more squaring is needed. In the previous case, in a BPSK case, after squaring itself, okay, we got a signal that is cos 2 omega 0t. So that signal is not available here. because addition of these two will become 1. So next remaining part is plus or minus 1 ps sine 2 omega 0 t. If this plus or minus 1 is not there, then this signal can be used for regenerating carrier. But that is not the case here. With sine 2 omega 0 t, there is a plus or minus 1. So this can be again cancelled using the second square. Again a plus b square plus b square plus 2ab. And in this term, ps square, it's a constant. Sine square 2 omega 0 t can be written as 1 minus cos 4 omega 0 t by 2. That is written here, ps square by 2 minus ps square by 2 cos 4 omega 0 t. And the last term is written the same way. Now the frequency of first term is 0, frequency of second term is 0, frequency of third term is 4 omega 0, and the frequency of the fourth term is 2 omega 0. And if it is passing through a filter with center frequency 4 omega 0, output will be minus cos 4 omega 0 t. From that, frequency divided by 4, so we will get minus cos omega 0 t. From this minus cos omega 0 t, using phase shifting circuit, sin omega 0 t and cos omega 0 t can be obtained, and that sin omega 0 t and cos omega 0 t I am showing here. These are the phase quadrature carriers regenerated from the received signal for reception. If the regenerated carriers are used for reception, then the receiver is coherent receiver or synchronous receiver. Probability of error will be minimum, but due to this complexity, the complexity of the receiver is maximum. And then the received signal is multiplied with the sin omega 0 t, then there is an integration. We will see the result of integration in the next slide. Received signal is again multiplied with the cos omega 0 t, again integration. And sine and cos signals are orthogonal signal, and that results we will see in the next slide. The first switch output S1 of 2 TB, that is also known as S1 of TS, integral 0 to TS, BOT root PS sin omega 0 t plus BET root PS cos omega 0 t into sin omega 0 t. So when you are multiplying, that is sine into sine, it will be sine square, and sine square and integration result will be TS by 2, that is TS by 2. And sine into cos integration result will be 0. So the second part is not written here. BOT root PS integral 0 to TS sine square omega 0 t dt. Sine cos product integration result will be 0 due to the orthogonality between sine and cos. So BOT root PS sine square omega 0 is half minus half cos 2 omega 0 t. Integration of half is TS by 2, integration of cos 2 omega 0 t equal to 0. That is due to the full number of cycles integration result will be 0. So the result is BOT root PS into TS by 2. This is constant, this is also constant, that is it is written BOT into constant K. Similarly, next multiplication is signal is multiplied with the instead of sine here cos. So once the cos is multiplied, first part will become 0 and only the second part we will get. That is BET into root PS into integral cos square omega 0 t dt, that is again root PS into TS by 2. That is written here BET into a constant K. So the first switch output is proportional to odd bit, second switch output is proportional to even bit. And we know these voltages are always plus or minus 1. This is also plus or minus 1. So the voltages we are getting at the output of that two switches are plus K or minus K. Now based on this, the decision can be made. If both are positive, that is K, output will be 1, 1. If both are negative, output will be 0, 0. Otherwise, the decision will be 1, 0 or 0, 1. Because if this is K, then that indicates that this voltage is plus 1 and that is an indication odd bit is 1. And if this is also positive, so even bit is minus 1, so the bit will be plus 1. So the combination will be 1, 1. So that is written here. If both are positive, output will be 1, 1. If both are negative, output will be 0, 0. Or according to this combination, it will be 1, 0 or 0, 1. So at every 2 TB second, we will get odd bit or even bit. In a QPSK, odd bit and even bits are parallel. That is why that integration is also the same for the same interval 0 to TS. That is 0 to TS, next to TS to 2 TS, next to 2 TS to 3 TS, etc. But when it is coming to offset QPSK modulation, there is a difference of TB second between odd bit and even bit. That is why there is a small difference in that interval. So one interval will be minus TB to plus TB and the second interval will be 0 to 2 TB. That is, it is written like this: integral 2k TB to 2k plus 2 TB. Substitute k is equal to 0 here. So it will be 0 to 2 TB. And another interval will be 2k minus 1 TB to 2k plus 1 TB. Substitute k is equal to 0. It will be minus TB to plus TB. So here it is always constant. For a QPSK, it is always same. 0 to 2 TB, then 2 TB to 4 TB, then 4 TB to 6 TB, etc. But for offset QPSK, this difference will come. Odd bit from minus TB to plus TB, then plus TB to plus 3 TB, then plus 3 TB to plus 5 TB, etc. That's a location of odd bit. And even bit 0 to 2 TB, 2 TB to 4 TB, 4 TB to 6 TB, etc. So this difference we should write here when you're doing integration, but the answer remains same. That answer is based on that interval. Interval is 2 TB second, that is TS second. So when you're making the block diagram of offset QPSK, just remember this difference. This difference we should show when you're showing that integration sign. Otherwise, same block diagram can be used for QPSK or offset QPSK. Both receivers are same. Power spectra density, power spectrum, bandwidth and spectral efficiency. PST of baseband signal is written here, and the baseband signal is plus or minus 1 with interval 2 TB second. Here the general result is written here. Amplitude plus or minus A and duration TB second. So the PST is A square TB sinc square FTB. But in our case, this A square is just 1 only, because A is equal to plus or minus 1. And the duration is not 2 TB second, duration is not TB second, duration is now 2 TB second. So that is written here, TB become 2 TB and A is equal to 1. So GBF is equal to 2 TB sinc square F2 TB. And the PST of carrier is PS by 2 del F minus F naught plus delta F plus F naught. Now, for getting the PST of QPSK, we need the convolution between these two. For doing convolution, first constant should be multiplied. So 2 TB into PS by 2, that is PSTB. It is written here PSTB. Next, sinc square F2 TB convolution delta F minus F naught. So only replace this F with F minus F naught. So answer is sinc square F minus F naught into 2 TB. Similarly, the convolution between these two signal, that is sinc square F plus F naught into 2 TB. So that's the PST of QPSK signal. PSTB sinc square F minus F naught into 2 TB plus sinc square F plus F naught into 2 TB. Now previously we studied how to draw the spectrum. First do the substitution. The entire term is equal to 0. F minus F naught into 2 TB is equal to 0. I am showing the result here. F minus F naught into 2 TB is equal to 0. Then F minus F naught is equal to 0 and F is equal to F naught. That is why at F is equal to F naught, we will get the center point of main lobe. Center point of main lobe we are able to get after this substitution. F minus F naught into 2 TB is equal to 0. From that, get the value of F. So we got the value of F is F naught. So that is why at F is equal to F naught, we will get the center point. Next, one more point is needed where we are getting this null point. For getting this null point, substitute this term is equal to 1. I am doing the substitution here. F minus F naught into 2 TB is equal to 1. Then F minus F naught is equal to 1 by 2 TB. Then F is equal to F naught plus 1 by 2 TB. That is same as F naught plus FB by 2. That is why here F naught plus FB by 2. Once we got these 2 points, the same width is going to be repeated. So this width is FB by 2. So again go for a plus FB by 2. From here minus FB by 2. Again minus FB by 2. Same thing, the mirror image will come here, that is a minus of that one. Minus F naught, then minus of this, that will be minus F naught minus FB by 2, and minus of this, that is minus F naught plus FB by 2. When F is equal to F naught, substitute F is equal to F naught here, it will be sinc square 0. Sinc square 0 is equal to 1. 1 into PSTB. That is why at F is equal to F naught, the height will be PSTB. I think it is clear how we can draw the spectrum once you know the PSD. X-axis frequency, Y-axis PST. This is called the power spectrum of QPSK. From this power spectrum, get the width of the main lobe, that is a minimum bandwidth. F0 plus FB by 2 minus F0 minus FB by 2. That bandwidth will be FB Hertz. So QPSK bandwidth is FB Hertz and spectral efficiency is bit rate upon bandwidth, that is FB bits per second upon FB Hertz. So it is 1 bit per second per Hertz. Previously we got for BPSK it was 2 FB Hertz and spectral efficiency was 0.5 bits per second per Hertz. So the advantage over BPSK, we can see here only the half bandwidth is needed or the spectral efficiency will be doubled. That is the main advantage we are getting from QPSK compared to BPSK or BASK or BFSK. Spectral efficiency is more. When we are saying the bandwidth is FB Hertz, what is the meaning of this one? For transmitting 1 megabits per second, we need 1 megahertz bandwidth using QPSK. But if you are using BPSK for transmitting 1 megabits per second, BPSK needs 2 megahertz bandwidth. BASK also needs 2 megahertz bandwidth and a BFSK needs 4 megahertz bandwidth. That is the advantage we are getting from QPSK modulation. Now, probability of error, Euclidean distance and signal space diagram. Signal space diagram is also known as geometrical representation or signal constellation diagram. So there are only 3 steps for this. First you write the expression of QPSK, that is root 2 ps cos of omega 0 t plus 2i plus 1 into pi by 4. This is expression of QPSK. And then write the normalized reference signal. Just change the amplitude, that's all. Normalized amplitude will be root 2 by ts. So that is written here, root 2 by ts. Why it is root 2 by ts? Because when you are calculating the energy of this signal over the interval ts second, it will become 1. That is why it is called normalized. So root 2 by ts cos omega 0 t plus 2i plus 1 into pi by 4. Second step is over. Now the third step, write the first equation in terms of normalized signal like this. Root PSTS into root 2 by ts cos of omega 0 t plus 2i plus 1 into pi by 4. After the cancellation of ts and ts, you can see the same result we will get. So there is no difference between first equation and third equation. So what we are doing, the first equation is represented in terms of normalized vectors. Now along each normalized vector we will get 1 point with respect to this amplitude. That we are going to get here. First normalized vector is root 2 by ts cos omega 0 t plus pi by 4. After substituting I is equal to 0, pi by 4. So that vector is this one. This is that vector because x-axis is root 2 by ts cos omega 0 t. This will be plus pi by 4. So this is a vector. Along this vector you take 1 point with a distance of root PSTS from origin. So from origin this distance is root PSTS. So we got the first point. This is the signal point and it is representing 0, 1. This is clear from that initial vector representation. The first quadrant we got 0, 1, second quadrant we got 0, 0, third we got 1, 0, fourth we got 1, 1. So this is 0, 1 signal point. Then second will be substitute I is equal to 1 here, it will be cos omega 0 t plus 3 pi by 4, that is this vector, and along this vector also we will get 1 point with this distance root PSTS. So this distance is root PSTS. So like that we will get 4 vectors. Along each vector we will get 1 point, and from origin the distance remains same because this is constant, not changing. So we got 4 signal points. Now the minimum distance between 2 signal points is known as Euclidean distance. So minimum distance, so between these 2 distance is root 2 PSTS because here it is 90 degree. So this is root PSTS, this is root PSTS. So this length will be root 2 PSTS. So when I am taking these 2, there also you will get same answer. But don't take the distance between these 2 points. That will be 2 into root PSTS. That is not Euclidean distance. Euclidean distance is the minimum distance between 2 adjacent signal points. So we got dQPSK is equal to root 2 PSTS, that is again same as root 2 into PS into TS. TS is a simple interval and 2 bits are taken together, that is why it is written 2 TB. So root 2 into PS into 2 TB. Finally, it can be written as 2 into root PSTB or 2 into root EB. Probability of bit error probability. Probability of error, bracket I written bit error probability. Bit error probability means 0 is going to be received as 1 or 1 is going to be received as 0. For occurring that, what is the probability? That is half complementary error function square root of EB by eta. Substitute that. After substitution of d value, we will get that one. That is, the general result is half complementary error function square root of d square by 4 eta. And here d is equal to 2 into root EB. So d square will be 4 EB by 4 eta. So answer is half complementary error function square root of EB by eta. This also can be written in terms of quality, that is Q function, Q of root 2 EB by eta. Both are same. It can be represented in terms of complementary error function or it can be represented in terms of Q function. Then there is one more error probability we should say here, that is probability of symbol error. What is the meaning of symbol error probability is, what is the probability that this symbol is going to be received as this or this? I am not taking this one. The reason is that distance is more. So once you transmitted 0, 0, and what is the probability that it can be received as 0, 1 or 1, 0? And if it is received as 0, 1 or 1, 0, we will get only 1 bit error. That probability is already calculated. Now, there are two adjacent symbols with respect to each symbol. That is why the probability of symbol error will be 2 times compared to the probability of bit error. If this third symbol is also with the same distance with respect to 0, 0, then here the multiplication will be 3 into PB. But that is not the case here. Here, with respect to any one symbol, there are only 2 adjacent symbols. If there are only 2 adjacent symbols, then 2 into probability of bit error will be PSE, probability of symbol error. And the answer is error function complementary square root of EB by eta. That again can be written as 2 into Q of root 2 EB by eta. I think the difference is clear. Bit error is transmitted 0 and received 1 or transmitted 1 received as 0. That is known as a bit error. But the symbol error is 0, 0 is received as 0, 1, 0, 0 is received as 1, 0 or 0, 0 is received as 1, 1. That is known as a symbol error. But with respect to the minimum distance, 0, 0 can be received as only 0, 1 or 1, 0 because only these two are the adjacent one. That is why there is a multiplication 2 here, 2 into PB. If this point is also somewhere here with the same distance of root 2 PSTS, then we should multiply with the 3. And this was not calculated for binary system. The reason is for binary system there is no difference between bit or symbol. Both are same. So bit error probability and symbol error probabilities are same for binary system. The difference is only for 4 array system onwards. That is 4 array, 8 array, 16 array, 32 array, etc. M array system. The difference is there between bit error and symbol error. QPSK is very important digital modulation for many practical applications, especially for a cellular phone communication, paging, many wireless communication system. QPSK has been used. Thank you.